All right, I just had an OBS crash. Hopefully I didn't lose a lot. Let's see. So, right, when people figured out there was progress to be made by experimenting with different activation functions, well, they continued to experiment. They found a bunch of new ones. There was a flurry of papers where people published variants on ReLU and leaky ReLU. Several of them made progress. The biggest one that I'm aware of before the one we're about to talk about was called the Exponential Linear Unit, which is this thing. I have not read this paper because it's sort of not deeply fascinating. The Cliff Notes is basically this. This is the new function they discovered. This is the derivative. They observed that it's kind of shaped like ReLU. You'll notice that it's still x in the positive half, so its derivative is 1 and its value is x in the positive half, and then in the negative half it smoothly saturates. So it's bounded on the negative half to, is it -1? I shouldn't be dumb. I should know what it's bounded to down here, but I don't off the top of my head. I really should, because I'm looking at it. It's bounded to whatever the hell that is. I'm dumb. So it's bounded below. It smoothly saturates to the bound below. So it's a little bit like ReLU, right? Because ReLU is also sort of bounded low, right? But it's bounded to some negative value, and it can produce 0, right? It's 0 at 0, and then it's bounded to like -1 or -2 or whatever, right? And it smoothly bounds. And so there's a little region in here where its derivative is still going to be positive, even though it's, where its derivative will be positive, even though it's decreasing toward a bound. There it is, right? Okay, it is -1, right? So ELU smoothly saturates to -1 at negative infinity, but for positive inputs, it's still just x, right? So positive input is still x, positive derivative is still 1. In the negative half, it smoothly saturates to -1, which means that for the positive half, the derivative is 1, but for the negative half, the derivative sort of smoothly glides to 0, right? And this has a couple of behaviors that we might think are important, right? It saturates, which again, saturating is kind of important to having stable outputs, but for a certain range of negative values, right, it's going to have a positive gradient, so it takes it a little bit of time for the output to die. So if you keep your outputs bounded to this range, it will still be able to learn, right? It only saturates for fairly negative values, not small negative values. So yeah, we still have that nice solid error backflow for values greater than 0, and for a little bit of region of values less than 0, right? And here's a little graph of our error signal. So again, it looks the same as ReLU and LReLU for the positive half. No, don't do that. Stop that. It looks the same as ReLU and LReLU for the positive half because it's the same on those parts, right? It's x on this part. For the negative half, for a little bit, we have this little deebly boop here where our function is going down, right? Our function is going down and our error signal is increasing. But then, as we saturate, our error signal goes to 0, right? And again, I think a piece of wisdom, piece of learning from this might be try to keep your negative values, like the things you would expect to see in your negative values, in this range where you're still going to get an error signal with this thing.